right, everyone. Well, thank you for joining us for the webinar today. We are going to be discussing designing for weld reliability in aerospace and defense. Just a few notes to start with. We will be sending a recording of the presentation as well as the associated slideshow in the coming weeks after this webinar completes. Always feel free to ask questions in the chat as they come up, and we will be sure to answer all the questions at the end of the presentation. And as I'm sure you've noticed by now, all the attendees are on mute just to avoid any sort of background noise or any disturbances during the presentation. So we ask that you kindly stay muted throughout the presentation. And as we move through this, again, just feel free to ask questions in the chat and we'll make sure to get to them afterwards. So today presenting will be myself. My name is Corey Yeager. I'm the Director of Operations at EB Industries. And alongside with me, I have Dominic Rocco. He is the Senior Sales Engineer at EB Industries. So let's start by talking about why weld reliability really matters in aerospace and defense. So as most of you know, these parts that companies are typically manufacturing in the aerospace defense industry need to be surviving extreme conditions, things like high temperatures, high pressure. They really need to be able to withstand these conditions during production to make sure it's maintaining the functionality of the assembly. Also, another reason is just the general cost of weld failures. If there's a weld failure in the field, this might be satellites coming down, missions failing, launches failing. These things lead to program delays, scrapping parts, and just a multitude of mission-critical risks. And in this case, in extreme situations, we're talking about millions, if not billions of dollars on the line when failure is not an option. And in some of these cases, even human lives are at stake, and any failures could be catastrophic. And then, of course, there's also regulatory backdrop, things like ISO 9001, AS 9100, NADCAP, and many other accreditations could be at risk if these parts fail during production. So I'm going to pass this off to my colleague Dominic, talk a little about the design features.
Thank you, Corey. As Corey mentioned, I'm Dominic Rocco, Senior Sales Engineer at EB. First few slides up here are going to be more technical, so I thought I'd talk a bit about welding types and joint types to begin. This image on the slide, the bottom right image, shows some of the more common joint types that we see. The butt joint, the T-joint, which is really like a double fillet weld, the corner joint, when two walls kind of meet at a 90-degree angle, lap joints, which are overlapping of material that often have fillet welds joining there, and edge joints, which are more or less two thinner pieces of metal coming together. The joint design, the preferred method of joint design for us is a butt joint design with what we call a stepped joint, which is basically like a male and female type of step where the joint would kind of fit together like puzzle pieces. There's a couple of main benefits of that for us. One of them is that the pieces self-locate, which would eliminate the need for us to have to design and fabricate sophisticated alignment fixtures and things like that. But actually, the more critical benefit for us is that with the joint being stepped, it creates backing material for us for our weld to terminate safely into. If you look at the image with the normal butt joint design, it's easier for heat and the weld to kind of propagate deeper down the joint. And most of the times we're dealing with critical components under the joint and or material that's not compatible with welding. Access. The beam travels in a straight line and there must be unobstructed direct access from the power source to the weld joint. Most commonly, we're asked about adjacent walls and critical components that are located near the joint. The weld may, or I should say the objects in close proximity may absorb some of the beam power, resulting in discoloration and marking along the weld surface, or along the wall surface, I should say. We usually advise that critical items and perpendicular walls are about an 1/8 inch away from the joint. Fixturing challenges. The parts need to be held securely. And it sometimes plays a role in whether or not the job is really meant for us, or whether it's more suitable to be manually TIG welded. So yeah, we have to have a way of, especially with electron beam welding, because it takes place inside of a vacuum chamber, we have to have a way to hold the part securely and be able to maneuver it in a way that allows us access to the joint the whole time while welding. Next on the slide is material considerations: titanium, nickel alloys, aluminum, stainless steels, dissimilar joints. Really, my favorite thing to do is when a customer is kind of not flexible about the material, but they have some options, I like to have them give me a top 3 material wish list. And then I can sort of better discuss, kind of go through the list and talk about the welding properties and what would be best suited for us while still maintaining their, strength, corrosion resistance, weight, needs. All of those are really important factors in all different applications. Designing with welding in mind. Yeah, this is important. Tolerance stack up is obviously very important and maybe the least thought about while designing. It matters a lot in welding because it directly affects weld quality, fit up, and dimensional accuracy. That all depends on how precisely the parts come together prior to welding. Even small deviations can accumulate and cause major issues in the later stages of production. And our processes just happen to be mostly the final stages of manufacturing. So a lot of those tolerance stack-ups can matter quite a bit and affect us directly. Fusion welding in particular is extremely sensitive to gaps and misalignment, and part fit up is always critical for us. If multiple part tolerances stack unfavorably, you can end up with excessive gaps, mismatched edges, variable joint thickness, and poor weld penetration. All of these affect us directly. Most common mistakes. Well, the fixtures, for one, we have to be really diligent when we're designing and manufacturing the fixtures, making sure the fixtures do not block access to the weld joint. Both EB and laser, you need direct line of sight to the joints, or as I mentioned in the prior slide, you get those things will absorb the beam and pull away from the weld quality and the penetration that you're going for. Not accounting for the tolerance stack up, as I just mentioned as well. Selecting a weld joint type that doesn't match material thickness or process. For example, implementing a fillet weld where you require full penetration, where a butt weld would most likely be more suitable for that. Another common mistake would be underestimating the weld shrinkage and distortion. We commonly, and that's kind of why I added that picture of the spool valve on this slide. We've had a project in the past where there was a critical end-to-end length, and we have 2 rotary weld joints on the tubes. And as you can imagine, when you weld those 2 joints, it will pull the tube ends in closer, shrinking a bit. That would affect if you have a tight tolerance of plus or minus 1 or 2 on total length, that would obviously have a huge impact on that. Ensuring reliability throughout process control. This is extremely important to us. The beam parameters are specifically tailored by our weld engineers based on the joint design, material thickness, heat sensitivity. All of the factors that I've discussed on previous slides, our engineers go in with the knowledge of what could go wrong and how do I, design this beam to be most effective for that particular application. We're able to tweak the settings like power, feed rate, beam width, beam shape, etc. All will allow for slightly different beam variations. For example, if there's a critical item near the weld joint that cannot overheat, we might increase the feed rate, have our weld in the area for less amount of time. If we increase the feed rate, we may need to increase the pulse overlap if we're doing a pulse laser weld, but anything to kind of have that part absorb less heat as the weld goes by. Repeatability is paramount to us. Once the weld is developed, those parameters are locked into a validated weld schedule for subsequent use. And for the most part, we do not deviate from the weld schedule. There are, per the specs being used for different applications, there are slight variations within the weld schedule, but for the most part, that weld is considered developed. Fixturing and cleanliness are equally important. Without secure, reliable fixturing, the part could easily move. And part movement equals beam mislocation, and beam mislocation equals most likely a rejected part, or at least an aesthetic that we didn't mean to do. So yeah, dirty, oily joints will cause a weld failure, no matter how perfect the weld schedule is and fixture is. Cleanliness is first and foremost to us. And a rejected part due to contamination is 99% of the time going to be scrapped or deemed unrepairable. Once that contamination, machining, debris, oil kind of mixes in our weld pool, that sort of is the end of it there. It's generally impossible to kind of get away from that.
Right. I will talk a little about quality now.
Yes.
So again, now we've talked about how do you design a weld joint and how do you make sure that you've developed the right parameters to yield the right result for the functionality of the assembly. So now how do we ensure that the part has passed all the requirements and is going to work for the intended functionality again? So we usually will recommend a multitude of non-destructive testing. These will typically include visual inspection, X-ray, dye penetrant inspection, leak testing, etc. There are other ones that we also will use at times in the NDT process. But what this really is doing is this provides you with an extra layer of assurance that the weld will function as intended. You don't want to put a part into space without almost 100% certainty that it is going to work as intended. That could lead to, again, the catastrophic failures we mentioned earlier. So another key part of our process is a first article inspection and also a process qualification, similar to what Dominic was referring to earlier. Once that part has been dialed in, we want to make sure that that is qualified to the requirements necessary to consistently yield reliable parts in production. So what we typically do, especially for electron beam welding, we will almost always recommend performing a pre-weld sample. This can be done on a actual sample part that we help a customer design so that we don't, sometimes we'll consume a very expensive production unit, or if it's not cost prohibitive, we will also at times use an actual production component if it can be spared. Now, what this does is tells you that if the part is done the same way as sample piece, it should yield you similar, if not the same results from piece 1 to piece 1 million. And we also at times will recommend a post-weld sample, which is a sample that's done after the full lot has been completed, because that will ensure that what's welded between the two samples, as long as the parameters and the setup is done correctly, it should again yield you those same successful results. Really what this tells you is that extra inspection done during the development will protect parts during production. We have seen times where we have encouraged a specific NDT or testing method during development that has uncovered a problem that would not have been determined otherwise. For example, if a customer designs a part and the only inspection required is visual, what you may not find is subsurface deficiencies, things like porosity, undercutting, and those kind of things where you might end up leading to a failure in the field if it's not found during the inspection process. So just a couple of examples of things that we have supported over time, and the ways we've supported these projects is in a variety of ways, including weld joint design, material selection, and testing criteria. So a couple of examples, and there are a number of others as well. We've been in business for 60 years, so we've been doing this for quite some time now. But a couple of the top examples are thruster valves and controls, missile components, and defense system hermetic seals. So we do a lot of hermetic sealing here, which again, as the name sounds, is intended to produce a part that is fully hermetic. So in that situation, unlike the electron beam welding in some cases, we will recommend a helium leak test that we do through a mass spectrometer. So What we also will always recommend is please involve us in the design stage. We will find at times that we've helped customers save a lot of time and a lot of money when they've designed something where it looks great on paper, but in terms of actual manufacturability, it lacks. And we've always encouraged our customers and prospects and people who are looking to design welds just to get us involved early on, because we may help you save some money and time and headaches designing something that will not work in production. So just a little bit about us before we open up for questions. EB Industries is a full service provider. We do electron beam welding, laser welding, and laser hermetic sealing, which is laser welding inside of inert environment glove boxes. We also offer a suite of services that we, for value-added purposes, testing and the things mentioned earlier, also assembly, cleaning, heat treating in some cases. A lot of those processes we'll offer to make it an easier experience for our customers. And we've always met the requirements of component fabrication in using design, development, and production services. And as mentioned, we do also manage supply chain services to help produce complete assemblies. We have a 17,000 square foot facility in Long Island, New York, basically right smack in the center of it. And we support all of the United States, also Mexico, Canada, Israel, and various parts of Europe. And what do we really do? So now we actually will have 60 years of helping customers design weld joints for difficult precision welding challenges. We have an experienced set of engineers on staff to help us develop processes, develop the fixture, so on and so forth. And because of that, we have CAD, CAM, and solid modeling capabilities. We do the development here as well. We have a lot of experience and understand the importance of development, because we might be doing development jobs for several years before they turn to a production project for us. What's nice with us is that we have a large selection of electron beam and laser welding technology all under one roof. So if we try one thing, it doesn't work, we can move to something else, different process, a different type of laser welding, for example, different type of EB machine with different capabilities. It's all done in one area under one roof, so we can keep swapping back and forth as needed. We do have a machine shop on site to help us develop and design and fabricate fixtures for us. We also do our own metallurgical evaluation in terms of cross sections for penetration to determine any sort of subsurface deficiencies, as mentioned earlier. And we have a large network of suppliers and service providers that we collaborate with during the development process, that once we're in production and where, it's a smooth, well-oiled machine. And again, like most companies, we are obviously trying to be designed towards production. We like to be integrated and become part of the customer supply chain. We will like to offer solutions and suggestions, things to help improve the process. We don't just develop the job and walk away. We'll help you throughout the production process to make sure it's being able to be done as efficiently and as high quality as possible. We are ISO 13485, we're ISO 9001, AS 9100 certified, and we're NADCAP accredited for electron beam welding. We typically average between a 1 and 2 week turnaround, and we do have expedited services available as well. So our capabilities, we have multiple high voltage electron beam welders, as well as one low voltage electron beam welder. Our max chamber size is 3 feet by 3 feet by 6 feet, and several of our machines have 5-axis CNC controls. We also offer optional real-time parameter monitoring in some situations where that might be helpful for quality purposes. For laser welding, we have about 10 systems. These range from 50 watts to about 4,000 watts. We have pulsed and continuous wave lasers. We have fixed optics and fiber optics lasers, and almost all of our laser welding machines are multi-axis CNC controlled workstations. Now, for our laser hermetic sealing, again, which is laser welding inside of inert environment glove boxes, we have 2 glove boxes. One is a mixture of nitrogen and helium, and the other one is a mixture of argon and helium. That one is more intended for titanium welding. These ovens are equipped with automatic vacuum bake ovens that are capable of producing reports for us to prove the part was vacuum baked at the right time, the right temperature, and under the right conditions. And these machines are also computer-controlled environments with parameter monitoring and data logging capabilities. So alongside our welding, we also offer a suite of associated supporting services. For engineering, these include weld engineering and joint design. We do tool design and fabrication in-house. We can also help design systems and develop them as well. We do material and component sourcing, and we perform metallurgical evaluation using our cross-sectional analysis laboratory. We also offer pre and post welding services, things like cleaning and assembly, testing, heat treating, NDT, including X-ray and dye pen, mostly any contract manufacturing services, as well as other things like coating, anodizing, passivation, post-weld machining, stress relief. Whatever we can't do on site, we will help you manage that process through a third-party provider that we have a lot of experience working with. So for quality, again, which is a big aspect of this presentation, we are approved of a lot of OEMs and tier one suppliers. Also, as mentioned before, we're ISO 13485, AS 9100, ISO 9001, and NADCAP certified. We also, for electron beam welding specifically, we are certified to weld in accordance with AWS D17.1, AMS 2680, and AMS 2681. And our equipment and operators are certified to MIL Standard 1595 and also AWS D17.1 in turn. Now, for our experience in the industry, I'm just going to rattle off a couple of applications we've done in the past. For aerospace, space, and defense, we've done a lot of commercial and military aircraft engines, rockets, satellites, submersible componentry, sensors and controls, ordnance, and weapon systems. For the medical industry, we've done things like medical instruments, surgical tools, implantable devices, artificial joints, and dental appliances. And we also manage supply chain processes required to make this a complete assembly. Now, for some other industries, now again, these change and add all the time. We get different applications, very often for us. But a couple of the big ones that come to mind are battery, RF and microwave, automotive, food and beverage, nuclear energy, oil and gas, green energy, private and government research, semiconductor, and really wherever precision welding is required, we've done it before. Now, what separates us from other companies out there? The number one thing we always say is our quick turnarounds. As mentioned before, we're typically averaging in the 1-2 week neighborhood, but we also do offer same and next day commencement expedited services. We are also, as evidenced in this presentation, we do complimentary engineering consultation. We do that to help support the weld joint design process, as well as in some cases even help design the part itself to make sure it's being designed with all the manufacturing characteristics in mind that are required to meet the specifications. And again, as mentioned before, we are certified to many industry specifications, as well as customer OEMs, large OEMs. Those can be provided upon request. Other service offerings, we also expanded our offerings to include TIG welding. That helps support some applications that are good for parts that have gaps, that have rough cuts, and difficult to access weld joints. We also now offer laser marking that helps consolidate the supply chain and keep it all in one area. We also offer laser ablation, which is basically a laser process that removes rust off the surface of customer hardware. We also use that device for internal maintenance as well. So here's just a snapshot of some of our customers. And again, there's many, many, many others besides this, but this is just a kind of a mixture of different industries we support. Companies like Raytheon, DePuy, Lockheed Martin, Stryker, Aerojet Rocketdyne, Applied Materials, Abbott Labs, BAE Systems, Northrop Grumman, Boeing, and many others. Now, again, just to reiterate the percentage for today, we're myself, Corey Yeager, and Dominic Rocco. We've listed our contact information here in case you want to contact us after the presentation. And again, just a reminder, we will send this presentation out within the next week or two once this has been completed. So you don't have to kind of take notes now in real time. We'll make sure we give you guys the contact information so you have it after the fact. Now, I see we had a couple of questions in the chat. We had, Dominic, one person had asked, do we always weld in a single pass or do we do multiple passes in some cases?
Yeah, I like that question. We actually don't get asked that too often. Most of the times the welds are done in a single pass, but not all of the time. A lot of the times the electron beam welds will be so deep and require so much power that the top surface is less than desirable aesthetically. There may be a lot of weld buildup and weld BBs that occur due to that much power hitting down the weld joint and kind of having no place to go at some point and spitting back upwards. So at that point, we might do something what we call a cosmetic or a dress pass, which is more of a defocus beam with lower power. And that's really kind of just to smooth over everything that kind of occurred on the surface. Some applications don't require that. If it's an application that's going to go back to our customer for final machining, that cosmetic pass doesn't really matter all that much, so we won't do it. And in another instance, if we're welding materials that are known to maybe produce pinholes or maybe a little more porosity within the weld joint, we may go and do a second pass on that weld and kind of re-stir up all the just kind of re-stir up that weld pool and kind of try to cook out some of that additional porosity that we saw down in the joint. We usually see things like that when we cut the physical section and take a look at the welding section, and we have ways of measuring each pore, and that kind of gives you an idea about how much porosity is in the total weld.
So a follow-up question just came in. There's another question, but this one's more pertaining to the first one, so I'll ask that now for you, Dominic. Someone had asked, do dress passes help relieve retained stress?
Dress passes to me are more cosmetic. There are ways to design. There are ways we could talk about designing the part to kind of help relieve stress. And there are, in a lot of cases, if it's going to be considered a highly stressed joint, we may suggest designing what we like to call a weld relief groove that's sort of machined in adjacent to the weld joint. That machine groove may kind of mitigate how much the weld shrinks and distorts a bit, taking a lot of the stress off of the weld joint. The dress pass itself, I'd have to go back and take a look. There may be some dress passes where maybe it has more to do with structure than it does cosmetics, but most of the times it is cosmetic.
All right, thank you. So I see another question here where someone had asked if parts sampled are sometimes physically tested for mechanical properties, and they especially ask for dissimilar metal applications. Now, I do know that we do have applications that we have to do things like torque testing and even hardness testing in some cases, because people want to compare the pre-welded condition with the post-welded condition to make sure, again, similarly, the stress and the mechanical properties haven't changed. Sometimes in cases, that's why a specific material combination is selected for those mechanical properties. And people want to make sure that it's not going to affect those characteristics too much, where, again, over time, it might degrade the quality of the weld and even the parts themselves. So we do have cases where we are torque testing, hardness testing. In some other cases, we've done tensile testing, bend testing. Usually those are more of a coupon capacity, because hardness testing and, well, more so torque testing can be done to like a proof load, not for failure. So it depends what the application is, because some of those mechanical tests can be